Welcome to Chapter 4 of Class 10 Science, Carbon and its Compounds. In this fascinating chapter, we'll explore why carbon is such a special element that forms the basis of all living organisms and many things we use daily. Look around you, the food you eat, the clothes you wear, the medicines you take, and even your own body are all based on carbon compounds. In Activity 4.1, we list items we've used since morning and discover that most belong to the amazing world of carbon chemistry. Throughout this chapter, we'll understand covalent bonding, explore carbon allotropes, learn about hydrocarbons and functional groups, study important compounds like ethanol and ethanoic acid, and discover how soaps and detergents work. Get ready for an incredible journey into the chemistry of life. Let's begin by understanding covalent bonding in carbon. Carbon has atomic number 6 with electronic configuration 2, 4, meaning it has 4 valence electrons. It needs 4 more electrons to complete its octet, but it faces a dilemma. It cannot form C4- anion because 6 protons cannot hold 10 electrons comfortably, and it cannot form C4+ cation because removing 4 electrons requires enormous energy. Carbon solves this problem by sharing electrons through covalent bonding. In single covalent bonds, one pair of electrons is shared, as in hydrogen molecule H2. In double bonds, 2 pairs are shared, as in oxygen O2. In triple bonds, 3 pairs are shared, as in nitrogen N2. Methane CH4 shows how carbon shares its 4 valence electrons with 4 hydrogen atoms, with each bond being a single covalent bond. This sharing allows all atoms to attain noble gas configuration. Now let's explore the allotropes of carbon, different forms of the same element with different physical properties but similar chemical properties. Diamond has each carbon atom bonded to 4 others in a rigid 3-dimensional structure, making it the hardest natural substance and a poor conductor of electricity. Graphite has carbon atoms arranged in hexagonal layers with each atom bonded to 3 others, leaving free electrons that make it a good conductor, and the layers can slide over each other, making it soft and slippery. Fullerene C60 has carbon atoms arranged in a football-like structure. Interestingly, diamonds can be synthesized in laboratories by subjecting pure carbon to high pressure and temperature. These synthetic diamonds are small but identical to natural diamonds. The different properties of these allotropes arise solely from different arrangements of the same carbon atoms. Carbon's versatility is truly remarkable. It forms more compounds than all other elements combined. This is due to 2 unique properties: catenation and tetravalency. Catenation is carbon's ability to form bonds with other carbon atoms, creating long chains, branched chains, and rings. Tetravalency means carbon has 4 valence electrons and can form 4 bonds. This allows carbon to form saturated compounds with only single bonds, like alkanes with general formula CnH2n+2, and unsaturated compounds with double or triple bonds, like alkenes CnH2n and alkynes CnH2n-2. Structural isomerism occurs when compounds have the same molecular formula but different structures, like N-butane and isobutane, both C4H10 but with different physical properties. Carbon's small atomic size and strong C-C bonds make its compounds exceptionally stable compared to compounds of other elements. Functional groups and homologous series help us organize and understand carbon compounds. Functional groups are specific groups of atoms that determine the chemical properties of organic compounds. Important functional groups include OH for alcohols, CHO for aldehydes, C double bond O for ketones, COOH for carboxylic acids, C-double-C for alkenes, and C-triple bond C for alkynes. A homologous series is a family of compounds with the same functional group but differing by CH unit. For example, the alcohol series includes methanol CH3OH, ethanol C2H5OH, propanol C3H7OH, and butanol C4H9OH. Compounds in a homologous series show gradation in physical properties but similar chemical properties. Nomenclature follows specific rules. Identify carbon chain length, identify functional group, and combine with appropriate suffix or prefix, removing final, e, if the suffix starts with a vowel. Let's explore the chemical properties of carbon compounds. Combustion reactions involve burning carbon compounds in oxygen to produce carbon dioxide, water, heat, and light. In activities 4.3 and 4.4, we observe that saturated hydrocarbons give clean blue flames while unsaturated compounds give yellow sooty flames due to incomplete combustion. Oxidation reactions convert alcohols to carboxylic acids using oxidizing agents like alkaline KMNO4 or acidified K2Cr2O7. Addition reactions occur in unsaturated compounds where atoms add across double or triple bonds, like hydrogenation of vegetable oils using nickel catalyst. Substitution reactions occur in saturated compounds where one atom is replaced by another, like chlorination of methane in sunlight. Each reaction type has specific characteristics and applications in industry and daily life. Ethanol and ethanoic acid are two important carbon compounds in our daily lives. Ethanol C2H5OH is a liquid with pleasant smell, used in alcoholic drinks, medicines, and as a solvent. It reacts with sodium to produce hydrogen gas, dehydrates to ethene with concentrated H2SO4, and oxidizes to ethanoic acid. Consumption affects the nervous system and coordination. Ethanoic acid CH3COOH, commonly called acetic acid, is a weak acid used as vinegar, 5 to 8% solution. It freezes in winter, earning the name glacial acetic acid. It undergoes esterification with alcohols to form sweet-smelling esters used in perfumes, reacts with bases to form salts, and with carbonates to produce CO2 gas. Both compounds demonstrate the practical applications of carbon chemistry in food, healthcare, and industry. Soaps and detergents demonstrate amazing chemistry in cleaning. Soaps are sodium or potassium salts of long-chain fatty acids, with hydrophilic ionic heads and hydrophobic hydrocarbon tails. In Activity 4.10, we see that soap helps mix oil and water by forming micelles, structures where hydrophobic tails trap oil droplets while hydrophilic heads face water. This emulsion can be rinsed away, cleaning the surface. However, soaps don't work well in hard water containing Ca2+ and Mg2+ ions, as they form insoluble precipitates called scum. Detergents solve this problem. They are sodium salts of sulfonic acids or ammonium salts that don't form insoluble precipitates with hard water ions. Activities 4.11 and 4.12 demonstrate the difference between soap and detergent behavior in hard water. Understanding this chemistry helps us choose the right cleaning agents for different situations. Let's review the key concepts from this chapter. Carbon forms covalent bonds by sharing electrons, overcoming its need to gain or lose 4 electrons. Allotropes like diamond, graphite, and fullerene show how different structures of the same element yield different properties. Carbon's versatility comes from catenation and tetravalency, allowing millions of compounds. Functional groups determine chemical behavior. while homologous series show patterns in properties. Important reactions include combustion, oxidation, addition, and substitution. Ethanol and ethanoic acid have significant applications in daily life. Soaps clean through micelle formation, while detergents work in hard water. Carbon compounds are fundamental to fuels, materials, medicines, and life itself, showing why carbon is truly the element of life. Undefined.